So I hope some of you have seen vectors before in your science class or elsewhere, maybe in math. But a vector is simply something that represents both a magnitude, some sort of number, and some sort of direction. Now, direction can also be measured as a number, but direction and magnitude are the two crucial aspects to a vector. And again, for example, let's suppose I want to represent a velocity vector going 100 kilometers per hour in the southeast direction. Your textbook chooses to note a vector by an arrow with both tips marked. That could be confused with a ray. They do it boldface, or they sometimes will say in context you can figure out. I like to do my vector notation, which other textbooks will use as well, with just a single tip on the arrow. So I could say that's a vector representing, say, 100 kilometers per hour in the southeast direction. Suppose I wanted to represent a vector 200 kilometers per hour in the southeast direction. Well, the direction's the same, but my vector then, I would simply make twice as long. So there's 200 kilometers per hour. We could also name a vector. How we name a vector is we can call them, and again, your text uses a boldface. It's tough for you guys to use a boldface when you write. But generally, you can call it with a letter. Generally, they tend to use letters toward the end of the alphabet. So I could call these vectors U and V. Now, again, we can kind of place and move a vector around as long as two vectors have the same magnitude, meaning length, and they're going in the same direction. We say those two vectors are equal. So assuming U, V, and W here all have the same length, and they're all pointing in the same direction, we would say that they are all equal. U equals V equals W. Talking about the magnitude of a vector, the notation is going to be as such. It looks like absolute value. Those are the absolute value symbols, but in your textbook, this is going to be a bold-faced U. So this would be read the magnitude of the vector U. And again, I like to put, and again, some textbooks will use this, is you use, just to indicate that you have a vector, you put that little single-edged arrow above your lowercase letter to name the vector. So here's my magnitude of U, or my magnitude of W, etc. Now, suppose we want to add vectors. We're going to call this the head-to-tail method or parallelogram method. Either method, there are two methods that you can do. Let's suppose I want to add vector A to vector B. What I do is place, making sure that I keep vector B the same length and pointing in the same direction. I'm simply going to put the head, place the head of vector A equal to on top of the tail of vector B, and then the resultant vector, I'm going A to B. The resultant vector is going to be from the tail of A up to the head of B. And we can view that as, let's say you've gone in this direction for this distance, and then you've gone for this direction, this distance. What's the result? Where are you relative to the beginning? Well, you've gone here. So that's called the head-to-tail method for adding the two vectors. I also could do what's called the parallelogram method. The parallelogram method, you should see half a parallelogram with what we just come up with up above. If I want to look at vector A plus vector B, I look at taking my vector A, my vector B, and then simply creating a parallelogram so that my other two sides are parallel to the given vectors and equal in length to the bigger given vectors. And then I say that the resultant vector is, well, I started, it's A to B. my resultant vector is the diagonal of that parallelogram. So suppose we have some vector W here that represents 100 kilometers per hour heading in the northeast direction. What would negative W, negative of the vector of W be? And intuition tells you it should be probably the same magnitude. I'm simply taking the opposite of something. And what's that? What's the negative going to do? And your intuition might suggest that, hey, maybe it's the vector that has the same magnitude, 100 kilometers per hour, but it's going simply in the opposite direction. In this case, if I'm heading here northeast, the opposite direction would be southwest. And indeed, that intuition is correct. That is how we are going to define the negative of a vector. And if you then consider what's the resultant vector if you take W and add to it negative W, you're going to get the zero vector as your resultant vector. I'm thinking about the head to tail method, that should make sense. If I've got W here and I use the head to tail method, that means I place the tail of negative W onto the head of W, keeping, again, negative W has to go in the direction it needs to go, so I've got to translate this up here parallel. If I put negative W here, what's my resultant vector? If I do W, head to tail, then do negative W, I get back to where I started from. I've gone nowhere. I'm at zero, the zero vector. So again, just to lead you through a little bit, if we take a look at the class exercises on page 422, let's just take a look at a couple of these problems. First question asks you, relative to the diagram given, which is a parallelogram, does vector BC plus vector BA equal vector BD? And if I want to look at BC plus BA as using one of my two methods, I've got BC here, and then note that BA is down here initially, but I could also translate it up here. It's going to be equivalent to, the vector BA is equivalent to the vector CD. So then if I use using my head to tail method, here's BA, CD is equivalent to BA, so then I'm going to add the head to tail here. So my resultant vector is right here, this length, this direction, which according to the diagram would be BD. So number one happens to be true. Let's take a look at number two. Number two here, I've got, it's asking me, does the magnitude of vector BC plus the magnitude of vector BA equal the magnitude of BD? In this case, I'm considering the lengths of the vectors. So basically what they're saying is BA is going to be equivalent to CD. So there's my BA magnitude up there. I've got my BC magnitude here, and I've got my BD magnitude here. And they're asking, does the length of this plus the length of that equal the length of that? Clearly impossible, because the distance between, shortest distance between 2 points is that straight segment. This distance has to be longer, so 2 clearly is false. And finally, let's take a look at number 5. It's asking me, is vector AO equal to vector OC? And for two vectors to be equal, they got to have the same direction and have the same magnitude. Well, clearly AO and OC have the same direction because they're on a single line segment, AOC, so clearly same direction. And then the question is the magnitude the same? Would O be the midpoint of AC? And the question is, the answer is yes, because you were given that this is a parallelogram, the figure's a parallelogram, and we know the diagonals of a parallelogram bisect each other, so that indeed O is the midpoint. So vector AO will be equal to vector OC.